question that I want to, I am interested in this problem is the following question. On average, on average, right? How many games until I stop playing? Right. I want to know on average. If I start with a number of cash, then how many games until I stop playing? That means, well, of course, we're calling I stop playing when either the total cash is $0 or $3. On average, I want to know how many games until I walk out. So the so this is a wording question in terms of math. That means we have, so we call it, let me set A to be, again, the set containing 0 and 3. Alright, we notify A to be that set. Then the question is basically asking for, suppose I start from X amount of cash. When is the first time I hit A on average? Right? I want to evaluate this expected value. And so observe following trivial situation. Suppose if I start with $0, can you tell me what that is? 0. If I start with $0, I don't play anything. I have to get out immediately, right? Because I stay at 0 forever, I don't really play anything. So this is equal to 0. Right? Similarly, if I start with $3, that is 0 as well. That is 0 as well. Right? So now so they are the trivial cases, and now I'm gonna focus on the more interesting case. So now concerning the other $1 or $2 and is for all X. Well, I guess I shouldn't say for all X here, just for X. For X, either $1 or $2, I have the following relation: expected value starting from X. BA can actually be written as 1 plus summation of PX Z, expected value of starting from Z VA. Alright, this is Z for Z in S. That is kind of like a general formula. But in terms of this particular example, that can be written as 1 plus, well, probability of going down from 8.6, so 0.6, multiply with X minus 1, VA, and plus 0.4 for going up, X plus 1, VA. So in order to see this, well, roughly speaking, you have something like this. Roughly speaking, all right. Let's say I start with the X, okay, and let's say this is Y, or maybe Z. And above here I have start with x times 0. In the next step is 1. So then we're going to jump up to z. We're going to jump up to z. More step. And that has to happen with that probability pxz. So this is pxz. And then start with z there. I will do whatever. But then at some time I will hit a for the first time. So let's say this is n. So this distance. Alright. This distance is b of a. First time a starting from x. Starting from x. And then this length right here is the first time hitting a starting from the z. And so of course we have the length here which is 1. Right? And so roughly speaking, that could be thought as in order to go from x to a for the first time, first I gotta take one step to some z, and then starting from z, I will hit a for the first time starting with z. And so of course I will hit z with this probability. So that's why, roughly speaking, I have this formula. So take one step, and then starting from that z with this probability, I will hit a for the first time. So, how do we really write this down in terms of math? It is the following thing. So, proof here, the claim I have the value of x. Okay, so this, I guess, let's say, so this is recalling, this is just by the definition of expected value, summation of k. Probability starting from x. I hit a for the first time in k number of steps. Right. So that is the original definition. So k starting from 0 to infinity. Yeah. But of course I will count k being 0. Because so so in principle this is the same as k starting from 1 up to infinity. K times this probability, EAB. Okay. So now I'm going to do the usual decomposition in one step. So this is sum k starting from 1, k times this will be probability, so summation on z. So summation on z in S. Probability of BA, B to K, starting given x1 B and Z, x0, B and little x, multiplied with probability x going to Z in one step. Yeah. So now we're going to reset the clock over here using the Markov property. This is the same as saying, forgetting the step 0, forgetting it. This is equal to probability hitting A for the first time in k minus 1, given x1 e, that's what x0 is z. So now, well, let me summarize what I have so far. This is the same as what. Right, let me rewrite this series. The summation on k starting from 1. And, well, I guess I could interchange summation. So I guess I could do this. I could sum on z first, and pxz stays here, and then sum on k. Okay, or really start with z, b a b and k minus 1. Yeah. We just change the order of the summation. Any questions so far? Please. Why is this?
What does the K represent? What does the K represent?
What is the K representing?
Like in the, yeah. Like what are you studying?
So VA is a random variable taking value in the integer.
Yeah.
So this is the definition of expected value, basically.
Oh, okay.
Right?
Yeah.
Okay.
What is that? Is that the case, the probability you give the other sample, the other random variable?
The other one, sorry.
Is the case about like just like the one you want in the plan? The k is equal to 0.6 and 0.4, something like that.
No, that is the probability.
Oh, that's the probability.
That is the something of
So k is the estimated value.
K is the value of VA. Yeah. Or you want to go with N maybe, if you prefer, go with N.
I don't think it matters now. I just
Yeah.
didn't understand.
Okay. So now, the things over here, if I rewrite the index on K, that is Z in S, P like Z. So that would be like what? That would be like, if I set, this is K minus 1, so that means I will start from time 0, and this becomes K plus 1. Probability of Z, B A B. Right. So I just change the index. So now I would just multiply through, distribute, I would say, the probability with the K plus 1, that is equal to summation on K, probability of Z, B A B and K, and then plus what? Plus summation of K starting at 0, probability of Z, B A B and K. Yeah. So up to this point, this is simply expected value of Z, starting from Z of VA. All right. That is that, and the other summation is the probability starting from Z, VA, B infinite. Right. Okay. And then, well, to note that I'm kind of cheating here, but this is actually equal to, this is actually equal to 1. Actually, that is equal to 1. I'm cheating there. That will be the theorem later on from this, but here, let's just take it for granted for now. All right. So, summarizing everything, I have a summation of Z in S, T X Z, expected value of Z, VA, well, of course, that sum right here is just one, and I recover the claim. I recover the claim. So let me revise that again. Summation Z and S, P and Z, the value of Z here, plus 1. Alright? S claim. So now to summarize, so now let me set G of X, B and respective value of X, hit A for the first time. Then what do I have? So I have G of 0 is the same as G B of 0, and I have G of 1 is 1 plus 0.6. Well, so 1 here, so going down 0 plus 0.4, G of 2, and G of 2 is 1 plus 0.6, G1 plus 0.4, G3. Right? And this is just a linear system of equation. And you can solve for G pretty quickly, I would say, so that you will be able to recover the expected time. I will stop playing. Here I have X star to begin with. Alright. Yes, please.
Over there, how do you know that the Markov property holds small d?
Right here.
Yeah.
So yes, I'm being a little bit sloppy here, but you can actually write it down more explicitly if you want to. But here, basically, I am forgetting the past using the Markov property. I will start from x1 star. I will start from z here. And so if I from little x going to a in k steps, that means if I start with z, I have to go to a in this number step, k minus 1.
But don't you have to show that BA is a Markov chain?
X is a Markov chain.
Or X?
The VA is a stopping time. VA is a stopping time.
Yeah.
Yes.
For this proof, we need X not to be in A, right?
Correct.
And we need X not to be in the set A. If X belongs to the set A, we cannot do that. Because
Of course,
X
of
cannot
course.
be zero. So
Yes, indeed.
what exactly did we use? it?
Right. So if X here already belongs to A, then this actually everything here will be 0. That doesn't make any sense here.
Okay.
Because if I'm already in A, B, A, B, and K for some K starting from 1, that is impossible.
Okay.
So everything is 0, and so actually everything is 0, so that is 0 for sure.
And for the sum being 1, we use the theorem, like the lemma in the last lecture, right?
Yes, sir. Indeed, indeed. If this is equal to 1, I will recall that in a moment. All right, but I will recall that in a moment. All right. Any other questions before I move on, guys? Yeah. All right. So now let me mention the theorem for the second completeness. Theorem is the following. I suppose I have an A and C joint. Just that S is the union of A and C. C is a finite set. Alright. I suppose further for S in C, I will have to hit, I will have to visit A finite time with a positive probability. Alright. Let me denote the function G as a function from S max to R satisfy the following condition. I have a floral x in A, g of x be at 0, and the floral x in the set C. I have g of x is 1 plus summation from p x z g of z. Alright, z in x. Then the theorem says G indeed exists uniquely. Here's something here. So the theorem says then this function G uniquely exists. And given by the formula g of x is nothing other than expected time starting from x, and the reason is a for the first time. Yeah. Of course, the proof here is out of scope, so let me just skip the proof. So now to go back and recall from the lemma last time that I mentioned, recall from the lemma, I believe, lemma 2, section 1.8. If C be infinite, contain only transient states, right? And every element in C is transient. Then actually we have a probability starting from x, be infinite, so I will have to hit a finite time. This is actually 1 for all x here. So then for all x in C, it has to occur with probability 1, which x pretty much explains this for this particular exercise example here. So let me move on to the last section of the book concerning infinite state space. Section 10. But let me recall from the two results above, recalling if I have the irreducibility plus recurrence, so I plus R, second result above there, then I know for sure there must exist a stationary measure, but it may not be normalizable to a stationary distribution. In other words, the sum of the mu y could be infinite, could be, right? So however, if you have S is finite, alright? Suppose I know S, the space is finite, then if I know further, irreducible, then basically I know everything. Basically, I know everything about S, about stationary distribution. If S being finite, satisfying the irreducibility, imply S must be recurrent. Now why is that?
Because the irreducible goes from x and y and y and x.
How do I know S being recurrent? Say it again.
The definition of the irreducible is the real x y and the real y x is greater than 0, so
Okay.
we come back.
So I come back.
Yeah, so very good.
There was a lemma around it. There was a lemma.
It's lemma 16.
Yeah. If the set is finite, then it must contain at least one recurrent vector. So you recall. Let me recall that result here. So if the set C is finite, then C must contain at least one recurrent state. Okay? That is one lemma. That means in S here, S must have at least one recurrent state. But now, if S is also irreducible, then everyone must be recurrent. And that comes from the second result saying X recurrent, and X could go to Y, then I believe then Y is, I should say, right? If X is recurrent, X and Y communicate, then the Y has to be recurrent. Alright, so in S, if I know S is reducible, everyone communicates with everyone, then one guy is recurrent, the rest has to be recurrent. Yeah, so that is that. So according to the results above, there exists a stationary measure mu, right? And furthermore, because S being finite, I can easily normalize it to be a stationary distribution, right? So mu can be normalized to a stationary distribution. Pi, say pi y is simply mu1 divided by summation of mu. See, we're seeing it now. Right? This is guaranteed. The sum is guaranteed to be finite because S is finite. Right? And in other words, I do have pi here, so in other words, that does imply irreducible plus recurrent plus an S pi. Right? So pi is unique. Pi is unique. So So if S being finite, I can pretty much say everything if I have reproducibility. Alright. So I should say, in particular, I guess for the sake of completeness, in particular, this, according to the first result, I have I, y being 1 over expected value of y, t1, which is positive, right? Because of this, it's mu positive, right? Yeah. And as a consequence, if 1 over this is positive, that does imply e y t1 is finite, right? If the 1 over expected value of t1 being positive, then the denominator has to be finite. Yeah. All right. So pretty much a lot of things you can say when you have irreducibility. So that is one way to go. So what if I don't have irreducibility? 2. If S is still being finite, does not satisfy the irreducibility, right? Then the pi will not be unique. Remember that pi is not unique. So S can be decomposed into T, transient states, R1, union 1, Rn. For each of this, I have a stationary distribution. Right? For each of the closed set of the current states, R of K, I have one stationary distribution by K concentrating in that RK. So, however, if Y is recurrent, alright, then that thing here still holds. Expected value of Y, T1 is still finite. Alright? Now why is that? Suppose S is not irreducible and Y is a recurrent state. How do I know the returning time on average is still finite? Yes.
Y must belong to some of the Ri, so we can apply the previous rule.
Yes, indeed. And so if Y is recurrent, Y has to belong to one of these closed sets. And it's concerning that closed set, let's say R1, you apply the previous results here. You apply this all the way along the table to the, say, R1 set. Alright? And you end up with this. So that is about the case as being finite. So now if I have the state space being infinite, so in general, right? In general, say if S is infinite, then Y recurrent does not imply the returning time is finite. cannot really apply anything about that. Pretty much case by case basis. Really. So nothing you can say if you have infinite state space. Right. So that's why they have to come up with the following definition to characterize that expected returning time. So given a recurrent state of y, right? And then let's say maybe from let's say we call y is called positive recurrent. If expected returning time is finite. Alright. If that is the case, the expected returning time being finite, then I'm going to call y being positive recurrent. On the other hand, y is called no recurrent. If expected returning time y is infinite. In other words, I know I have to go back to y. I know that. However, on average, I have to wait forever to go back to y. Okay. So let me give an example. On the fact that if you have a recurrent state, the returning time on average could be infinite. So the example that I want to pull out is the homework, problem 5b. Okay, probably you haven't taken a look at that, but let me give the following. Suppose I have a state space on 0, 1, 2. Okay, and I have the following condition matrix. From A going to plus 1 with this probability. So I believe that is plus 1 and plus 2. And going back to 0, going back here to 0 with the probability of 1. So to give to draw a picture. So I have 0 here, 1, 2, 3, so on. Alright. So for each, and I'm going to the right. Okay, 0 going to 1, 1 going to 2, 2 going to 3, keep going forever. And I could go back to 0. So starting from 0, I could go back to 0. 1 could go back to 0. 2 going back to 0. And 3 go back to 0. Okay? So the claim that I want to make is concerning the y0. 0 is no recurrent. That means I could go back to 0 for sure, but I could have to wait forever in order to go back to 0. Well, so there are two pieces in this statement. First one is to say 0 is recurrent, and the second is to say expected returning time to 0 is infinite. So the first piece, so step 1, 0 is indeed recurrent. In other words, I have to show, what do I need to show? I need to show probability starting from 0, t0 being infinite, is 0. Right? That is basically the definition of being recurrent. So I hope you guys still remember this probability is the limit, right? The limit of 0 to 0 greater than n and going to infinity. I hope you still remember that. Yeah. I have a decreasing sequence of events, and so the limiting is just the intersection. I'll work number 1. Calling this. So if I want to show this is 0, basically I need to show every term here is variable by something, and that something goes to 0, then I'm good. So you need to have a value on probability 0, t0 greater than, right? And that value has to go down to 0, then I'm good. So let's look at so probability of, let's say, start from 0, t0 is greater than let's say, n plus 1. Let's say. Okay. Returning time to 0 is greater than that. How is that possible? That is the same thing as saying x1 not 0, x2 not 0, up to xn not 0. Right? Yeah, pretty much. Now let me sketch it here. So 1, 2, 3, n, then n plus 1. So we'll go to the right, and let's go back. Now tell me a possible path satisfying this event. What is a possible path? A possible path satisfying this condition.
You multiply the probability.
No, just give me a path. Give me a path first. A path satisfying this condition. x1 not 0, x2 not 0, all the way up to this.
1, 2, 3, 4, 5, 6, 1 to n.
All the way to n, right? So one possibility is starting from 0, I keep going all the way to the right,
Yep.
up to n. Is there any possible path?
No others, because it's so one.
Is there any other way satisfying that condition?
No.
No, the answer is actually no. That is the only way. So actually this is the same as probability starting from 0, x1 is 1, x2 is 2, up to x of n is indeed n. That's actually the only way to go. Okay. if you're not so convinced, then you could claim saying, if I start from 0, x1 is not 0, then x1 has to be 1. You can say following. Suppose I have like x0 being 0, x1 not 0. This is the same as x not 0 and x1 is 1. Yeah. And then you can keep going. Say x0 is 0, x1 is not 0, x2 is not 0. Is the same as x0 is 0, x1 is 1, x2 is not 0. So if I start at 1 here, how is that possible? The next step is not 0. That is because I could only go to the right. Yeah. So this is the same as this, and then next 2 must be 2. And you keep going up until you exhaust all the way into this. Yeah. Anyway, so now this is the same as the product. P of basically you have k plus 1, k starting from 0 up to n minus 1. Right? And then you plug in the probability going to the right. You should plug in, and you'll be able to cancel out.
Yeah.
You'll be able to cancel out everything. And up to this point, so the answer will be something like, I believe,
1 over plus 2.
and plus 2.
That is what we can.
And well, so that means this probability is 1 over n plus 1. So indeed, this probability right here. Alright. You take a limit. Take a limit as n goes to infinity. That has to be 0. Right? So that is step 1. We will discuss step 2 in on Friday. Okay.
What does the last line say? The first